Hello, my name is Lukas Naehrig. I'm a sophomore studying statistics.
And hi, my name is Noah Asch. I'm a sophomore majoring in atmospheric science.
And we work with our mentor, Professor Dargan Frierson, to analyze simulations from 35 climate models that allow us to visualize and understand how to predict the global average precipitation rate. Understanding factors that determine global precipitation can help us interpret climate simulations of the future. Our goal is to explain the differences in precipitation across models, allowing us to better predict changes in global and regional precipitation as the climate warms.
We use Jupyter Notebook, a Python program, to run the climate models and analyze the data in multiple ways. The first graph we produced is the multi-model mean precipitation graph from 1850 to 2015. This is an average of 35 models. The noticeable yearly variability shows how sensitive precipitation can be to atmospheric conditions. For example, the dips in the graph, such as 1883 after Krakatoa, show volcanoes which give a temporary cooling effect to the atmosphere. Air pollution, which increased rapidly in the late 20th century, has the same effect. However, the greenhouse effects from pollution usually outweigh the cooling they produce to the atmosphere long term.
Moving to the precipitation time plot, which you can see in the top center of our infographic. This shows the yearly precipitation from each model. Notice that the increase in rainfall for each model is minute relative to the range of the precipitation rate across all models.
On the left side of the poster are the scatter plots of the surface and atmospheric budgets. Both the surface budget and the atmospheric budget can constrain global mean precipitation. These plots show an imperfect but adequate closure of the energy budgets, meaning we can use these budgets to explain precipitation change.
The bar charts on the right side of the poster show the decomposition of precipitation change into energetic terms that support either evaporation at the surface or latent heating in the atmosphere. The term that immediately jumped out to us as being best correlated is the sensible heat flux. Models with larger evaporation and precipitation have smaller sensible heat flux. We were surprised to find this because usually sunlight or the greenhouse effect is considered first.
We plotted the comparison of PR versus HFSS on the bottom left of the poster and confirmed a correlation of negative 0.612. When sensible heat flux is smaller, this allows more evaporative cooling at the surface and more condensational heat release within the atmosphere. The global mean sensible heat flux varies by over a factor of 2 among some models.
The second best correlated term we examined in any energetic budget was the net radiative cooling of the atmosphere, which is shortwave plus longwave, and that has a correlation of 0.453. The atmospheric radiation correlation is roughly equal due to shortwave and longwave factors. Additionally, we picked two different models from the CMIP6 database, which represent the two extreme ends of the HFSS range and generated contour plots of these models. On land, the exaggerated regions of HFSS seem to be in dry areas such as the desert regions in northern Australia and western Chile. However, there's a noticeable difference in sensible heat flux shown over the oceans as well. Both ocean and land contribute significantly to the difference between these models.
Building off of the contour plots, we decided to construct a plot of HFSS at different latitudes and noticed that the biggest range in variability between models was over the latitudes that encompassed a greater landmass. In future work, we'll look into differences in surface relative humidity, surface air temperature difference, and drag coefficient, as well as more detailed analysis of the energy budgets.
In conclusion, we realized that sensible heat flux differed a lot by model, leading to differences in precipitation. Other terms are quantitatively important in individual models, but explain less of the overall spread. Energy budgets are essential in helping us understand the ever-increasing precipitation in our warming climate.